It's been a long time, and I thank the organizers for giving me an opportunity to speak here. As you can see that I have slightly changed the title, and I did that because we have done some new work meanwhile, and I wanted to include that. Actually, I was thinking of a 30-minute talk, but then I found out that it is, 45 minutes and more. So, yeah, 40 minutes, yeah. So I sort of thought that, okay, maybe we can include it. At the risk of sounding a little bit pretentious, what I'm going to do here is not talk about a single problem, but we'll try to present a sort of point of view which should be useful for a variety of problems. There is a sort of common theme between this. And the three things that I have picked up here is origami, yielding of crystals, so that's the closest to the theme of this conference, and protein ligand binding. So basically I'll be talking about a lot of things except for fracture. So sorry about that, but I think this theme will be useful for that problem too. So okay, so let's go on, and the significance of this picture will be obvious later on. Okay, so origami, origami, pleats, folds, wrinkles, we know what they are. We have seen this in dresses. You can fold paper into various shapes and make animals out of sheets and so on. So all this depends on how you can fold a two-dimensional object into 3D structures, and this has become very useful recently because of its if you want to make complex structures and you want them to be also stackable, so that they can be stored in a very compact fashion. And then when you require it, you can unfurl it. So these sort of things you see in things like lampshades, which you can buy, and then it sort of flat folds onto a 2D sheet, and then you can fold it out. There's a sort of somewhat technical and scientific name to this. These are called Miura-Ori tessellations. So you can make these tessellations, and you can actually program the curvature depending on these angles, and all of these are so-called flat foldable. So these are, they can be completely flattened, and then as a single parameter, they can fold out. So the entire physics of this is basically how you pattern these it's a 2D object. Okay, so we need not think about the third direction because that's sort of trivial. It's just one parameter which you unfurl. So how do you do this for, let's say, a discrete lattice? So let's say we take a triangular lattice here, and then make a valley fold and a mountain fold here. You will see that I can fold a triangular lattice onto itself completely with no bond stretching or rotation, and this produces what I will call a pleat. So you can take something and then pleat it. So this is a little movie. Oops. I hope it plays, yeah. So this is a little movie how you can pleat this triangular lattice. So it produces 60-degree pleats and a horizontal pleat. And you can see that the 60-degree pleat involves a little stretching of bonds, but the horizontal pleat, it doesn't. You have to look very carefully for this. And usually, people think of wrinkles, pleats, folds, so on, as instabilities of a 2D surface. But here we are going to relate this to an actual phase transition. And if you look carefully, okay, so this maybe I can tell you later. This is a kind of this Miura-Ori tessellation, except that the length scales are much larger. Okay, so we'll come to that. Okay, so this is pleating. Then we come to plastic deformation. Completely different subject, and this is something which is rather well known. So you take a wire, let's say, or some sample, and you pull on it, measure stress versus strain. For small stresses, stress versus strain are linear. They're, it's proportional to each other. It's of course known as Hooke's law. But then at some point, the solid starts to deform irreversibly, and this is the plastic deformation, onset of plastic deformation. And people usually, there is some controversy, but people do associate this point with the yield point. Okay? And if you were to calculate, if you were to find out the yield point of various materials, this turns out to be much smaller than what you would calculate from a completely naive, energy consideration. So you take a ideal lattice and want to find out the energy required to shift one layer to make it flow, and then this energy turns out to be much larger than what you actually measure in the lab. And this used to be a big problem till it was solved by this great man, Geoffrey Ingram Taylor, who sort of predicted the occurrence of crystal defects known as dislocations. So as you can see that if the crystal is not ideal and it has a defect like this, then the energies required is much lower, because you don't have to shift the entire layer, you can shift it part by part, and all the energy that you have to pay is to cut a few bonds and make new bonds in a very local region. So this is the so-called celebrated dislocation theory, and most of our understanding of plastic deformation are, okay, why most? I mean, I should say that all of our understanding of plastic deformation in crystalline solids is based on this theory of dislocations. And it's been around for more than 60, 70 years now. And later on, dislocations have actually been seen in transmission electron microscopy. They are seen in computer experiments. They are everywhere. However, the plastic deformation of crystals is still a tricky business, and not too many people worry about it, but there's this beautiful paper and some byproducts of this paper which came out a few years back, and they point out something very curious. Okay, and the argument is like this. Suppose you take an ideal crystal and then you shear it. Okay, so once you shear it, the internal arrangement of atoms inside this changes. However, you can always rearrange the atoms back, okay, so that the shear stress goes to zero. The only cost that you pay is a surface cost. Okay, and this surface cost comes from putting in dislocations here, so that the rearranged crystal and the original crystal, they fit with each other. And you can always do this. Think about this. You have planes which have shifted. You can always shift them back. But once you shift them back, yeah.
So do you have plane boundaries?
This is a single crystal. But once you shift them back, you will have a boundary. And the energy will be completely localized at this boundary, where you have to put in dislocations. So now you can make a typical, first passage time like calculation, and from the time and from the stress which you have relaxed, you can calculate a viscosity, and you can plot this viscosity, and this viscosity turns out to be something like this, and then this has a essential singularity at stress equal to 0. So if you plot this object, okay, as a stress versus strain, you will see that this curve, it does not have any transition or anything, but there is a knee, and there is an effectively it is flat. So if this was really resisting stress, okay, so the idea is that a solid will resist stress. So if it really resisted stress, then this would have been flat. But it turns out that it is not quite flat. There is an essential singularity, but it is very close to being flat. So what this the questions that it raises is an important one. It shows that you can always reduce the free energy of a stressed crystal. You can always reduce the bulk free energy. You have to pay only a surface free energy cost in putting in dislocations. There is no singularity. So this whole business of yield point is just fake. You know, so there is no real singularity. There is a knee in the curve, and if you stress something, it sort of goes, it flows. Even a crystalline solid flows, but it flows at an extremely tiny rate which you can't measure. As the stress increases, this flow rate becomes measurable, and that is what you call as the yield point. I would like to emphasize this particular point, that it always reduces the free energy. Okay, and I would like to invite you to think about this already as the talk progresses. Okay, the third thing is again something completely different. So we look at proteins. Okay, so this is a very popular protein, and I'm sure this movie has been shown in this very hall many times. And this is kinesin walking on a microtubule while carrying a cargo. All that I want to point out here is that this is a protein, this whole thing, but the main sort of motions is concentrated here. So the rest of the protein is doing something, but the most important, the physiologically important motions are happening at a very tiny point. Okay, so with these three different problems, yeah. It's a computer simulation, I think. It's not an actual, yeah. Actual pictures would be white blobs on black background or something like that, some fluorescence, yeah. Okay. So now you can see a little bit of the theme that I am trying to sort of present here. All of these things, they undergo some special displacements. Okay, so we are going to define something which I call the NAP or chi or non-affine parameter. So this is a single collective variable which captures interesting deformations wherever they are. Okay, so we will see that this variable is actually related to the usual positions, okay, particle positions. So this is actually a thermodynamic variable like any other, and one can define a conjugate field to this variable. And we will see that this is very much like stress, but it's a very peculiar kind of stress. Okay, so once you define this variable and the conjugate field, we will show that pleating of a lattice, of a connected lattice, is very much an equilibrium phase transition, okay, in the presence of this conjugate field. Okay, so it's not an instability in this case, it is in the presence of this field, it's a phase transition. And we will show that yielding in solids, normal plastic deformation, is just a dynamical transition which is associated with an analogous phase transition. Okay. and then we will sort of understand this Saussure-Biroli-Kurchan calculation in a slightly different light. And the same with collective variable, which it also is shown to capture interesting conformation changes in proteins. So basically this is the theme, that we have a collective variable which picks out surgically the most interesting deformations in any physical process. So this is that, this is where the bird picture comes in. So you have this bird which picks out the food from grains of sand. It doesn't eat the sand, it just takes the food. So this is what we are going to do. So take any complicated process, but have a very well-defined method to capture the most important deformations in this. Okay, so what is this non-affine parameter? This is something which was introduced in the glass literature, maybe even a decade or slightly more back, and the concept is not very difficult at all. That suppose you have a set of particles and they have a reference configuration. This could be the ideal lattice, it could be anything. It could be inherent structures in a glass, it doesn't matter, and a coarse graining volume which you decide. It could be the interaction volume, something. So you look at all the particles in this coarse graining volume. If you deform this reference and make it something else by multiplying it by a deformation matrix, then this is an affine deformation. Okay, so you have multiplied everything by a single matrix. However, in reality, there might be shuffles inside. So within this coarse graining volume, the deformations cannot be described only by an affine deformation, but there will be some extra little piece. So how do I find out this extra little piece? What do I do is that I minimize the actual deformation and the model which uses just affine deformations, and just minimize the error. Okay? And the sum of the squares of this error is my non-affine parameter, once minimized over local deformations. Now it's crucial to understand that this is something that we introduced in the game, is that this minimization is actually equivalent to a projection. If you take the displacement and you project them by a well-defined projection operator which depends only on the reference configuration, that is equivalent to minimizing this chi. And you can actually write down what this projection operator is as soon as R is known. So for any R, I can write down the projection operator. Okay. So once I have a microscopic definition of this non-affine parameter, one can calculate expectations, values, distributions, full spatio-temporal correlations, response function, everything like any other standard thermodynamic variable. For example, the thermal average of the non-affine parameter turns out to be just a trace, and it is a trace of PCP, where C is just the displacement correlator. So if you calculate the displacement correlator and project it, then the trace of that, the sum of the eigenvalues, gives you the non-affine parameter. So the English definition is, it is the trace of the coarse grained and projected matrix of displacement covariances. Very simple. Okay, and you can do it locally, and you can calculate global values, whatever. And if you have a simple Hamiltonian for which you all know the dynamical matrix, then you can calculate things exactly. So this is our calculations for a permanently bonded harmonic triangular network. That's just one of the simplest non-trivial crystalline solids that you can imagine. Dots are simulations, lines are exact theory, and as you can see, they are exact. You can calculate correlation functions of both the non-affine and the affine part, and you can show that continuum elasticity theory with its equations of mechanical stability as well as Sen-Venance compatibility conditions, all of it falls out from this. So this is all, it is compatible with compatibility. Okay, so continuum elastic theory is recovered from this. Okay. Okay, so now there is one more concept that I need to introduce before we can go on to results, is the eigenvalue spectrum of this PCP. Okay, so this actually connects us with what is normally known. Okay, so we know that this non-affine parameter is the trace of this matrix. So it is the sum of the eigenvalues of this projected correlator. But it is useful to look at the spectrum of these eigenvalues. So suppose I have colored here 3 different coarse graining volumes in the triangular lattice. This is the nearest neighbor, next nearest neighbor, and the third nearest neighbor. And my projection operators, everything will depend on this coarse graining volume. And this is the spectrum of eigenvalues. So you can see that there is a lowest eigenvalue. So this is actually the highest eigenvalue. I am plotting sigma inverse just to make it look like energy levels. And you can see that there is a lowest level, and then that is separated by a large gap. Okay? And if I increase the coarse graining volume, what happens is that all the upper energy levels gets filled, but this gap remains. So there is a big difference between really the most probable non-affine motion, which is represented by the lowest eigenvalue, and all the rest. Okay. So let us look at what contributes to this lowest eigenvalue, this highest eigenvalue. And these are the eigenvectors associated. So it's a degenerate. There are 2 degenerate eigenvectors. And you can see that in the triangular lattice, what happens is that basically it stretches nearest neighbor bonds, and it tries to bring 2 next nearest neighbor particles together. So if I were to replace, if I were to continue this, so that this becomes, AB becomes much larger than CD, and then I form this, I cut this bond and I form a bond between C and D, this is exactly a dislocation dipole. Okay. So dislocation theory, it comes out as a lowest eigenvalue approximation from this entire thing. Yeah.
When you talk about AD or AP
Yeah.
or AC,
Yeah.
I mean, at the level of electrons, they may not be a bond at all.
Sure, sure. So I am using a little bit of a, yeah. So all that I wanted to say really is that change in local topology of atoms, regardless of how the interactions come about, whether you have actual bonds or it is mediated by some electrons, change in the local topology of atoms is governed by this non-affine parameter, and the most probable, the most probable non-affine motion is just changing the local topology.
So let me understand and
Yeah.
correct me
Yeah, sure.
if I'm wrong. So originally, when you look at a point, an atom, and you construct the nearest neighbor, you have a Voronoi cell.
Yes.
What you have done is you have changed the Voronoi cell.
What I have done is I have found out the motion, that part of the displacement of atoms which would change the Voronoi cell. Okay. Yeah. So yeah. So this will have some consequences. Yeah. These are the other eigenvalues, and you can see that they are much more complicated. Okay. So now this is really it. If this non-affine parameter is just dependent on particle positions, I can simply define a field which is conjugate to it and attach it with the Hamiltonian. Okay. So think about this. You have displacements and you can look at the affine part of the displacement. And then you can add a term in the Hamiltonian which is the affine part of the displacement multiplied by the field. This is just stress because the affine part of the displacement is just strain. So this will be like this extended Lagrangian whatever, where you add to the Hamiltonian a stress into strain.
So there is no n-harmonics.
It doesn't matter. It doesn't matter because this really does not, exactly like you can take any Hamiltonian and put stress into strain, okay, and then do simulations, for example.
Because I think, you started with the yielding point, and, when you come to the yielding point,
of course,
n-harmonic effect.
of course, but the formalism does not depend on the interaction.
But what is scale?
Oh, just wait, because I am going to make that statement, yeah. So, okay, so let me press enter. Oops. So what I wanted to say is that this part can be replaced by any damn Hamiltonian you want. It doesn't really matter. Now, we will show results for a harmonic Hamiltonian because here you can get analytic results, but you can in principle replace this by anything. Okay, so the only new thing is this extension, and what I want to argue is that this extension is exactly like stress into strain, but instead of stress into strain, you have the non-affine part of the displacement, which is the non-affine parameter multiplied by a conjugate field. Okay, so this is a new kind, yeah.
But you minimized something before computing the non-affine parameter.
Yes.
And so you minimize what? The energy?
I will what?
Minimize.
Minimize. Oh, we minimize the, so that is minimization of the error in trying to fit a strain to a configuration. But I said that this minimization process is taken care of by projection. So once I have the projection matrices which go into the definition of chi, okay, then there is no minimization involved here at this stage. It's all done. It's all done in this matrices. So as you can see, this is a typical, three-body interaction. You have uj, ui, uk, ui, and then p, I, j, k. Okay, and this matrix is a constant. So this is something that you can put in a simulation, okay, without a problem because you can calculate forces. They will be slightly complicated, but so what? I mean, people know how to handle three-body forces, okay? And you can see what happens once you put in this. So it is like putting something in a non-affine field. All that would have been okay. I mean, if it was just something that you do in a computer, it's not that interesting. But it turns out that you can actually generate this field in the lab. And this is something that we are talking about, talking with colloid experimentalists. And the idea is this. So nowadays it's very simple to get particle coordinates using video microscopy in a colloid. Okay? So you get these particle coordinates. You can calculate forces. This you do in a computer, so it can be done very fast. And then you have a set of laser traps. Okay? And you can construct displaced laser traps to apply exactly the force that you want. Okay, and you can repeat this at a frequency which I am told you can do this at 600 hertz, which is much faster than any time scale of motion of a standard colloidal particle.
But the laser trap,
Yeah.
it would be on the scale of a micron, whereas
No. Here you can do this only for colloids. You can't do it for an atom. Yeah. That maybe sometime deep in the future. But right now, you can do this only for micron-sized colloids. Yeah, you're absolutely right. There are other ways to generate this non-affine field, and I'm not going to go through this, but I can just tell you that active forces can also generate non-affine field. So all that I wanted to show here is that whatever I did to that Hamiltonian, this new extension, that is not completely hypothetical or completely mathematical. One can actually realize this in experiments if you work a little bit hard. Okay. So what happens if you put in a non-affine field? So what happens is, of course, depending on the sign of non-affineness, you can increase this average non-affine parameter or decrease it. Okay? And what really means is that you can actually use this thermodynamic field to tailor the probability of those fluctuations which are going to cause defects. Okay? So it's not directly that you are introducing defects, but you are slightly biasing those displacement fluctuations which will produce defects. And in simulations, this is exactly what it does. So you can control defect density in a colloidal crystal by using this non-affine field. And that has very important consequences. And the other thing that I should have written here is that you can do this without touching the elastic constants. Because non-affinity and elasticity, they are two orthogonal projections, you can do something to one part without at all, to linear order without at all affecting the other. And we'll see some consequences of this. So this is the first result. Okay? So this is what this is what happens for small values of the field. So when the field is increased, and this is interesting, this is the first interesting result. If you started with a bonded network where dislocations can't really form, okay, what the network does is that it pleats. Okay, it forms these pleats. And if you look at the free energy, so we do some fancy Monte Carlo techniques, this sequential umbrella sampling, and you can actually calculate the probability distribution of this non-affine parameter, and you can actually plot them, and inverse log of that looks like a free energy. So for small values of the field, there is only one minimum, but as you increase the field, there are other minima which appear. And then at some point, there is a very, very typical first order transition. Okay? And I would like to point out that there is a saddle point, and the value of the non-affine parameter at the saddle point doesn't seem to depend on the field. So there is one saddle point which is the maximum non-affineness that a crystal can take, or that an ordered structure can take. And once it is exceeded, then it forms a pleat. And this pleating transition has a finite size scaling like any other normal first order transition. But let's look at some of the pleated configurations, and you can see that this is this configuration which we already talked about earlier. And if you compare it with these Miura-Ori tessellations, then it turns out that each of these minima are some tessellation. Okay, so there are infinite number of tessellations possible with different length scales, and they all, the conjecture, okay, so we have seen a few, and the conjecture is that all of them are there in this parameter space somewhere. It depends on, the... This is all 2D.
So we are not looking at the projection.
Yeah, no, this is 2D. What I said in the beginning is that these Miura-OD things, these are flat foldable. So the third dimension is that you can just unfold. So you need not look at that. You can just concentrate on 2D. So this is, you can get these things by histogram reweighting in the usual way that you study first order transitions in a simulation. And you can see that, it has this beautiful lever rule and an interface between two states where, so this color here is the stress. So in one state, the stress is homogeneous, and in the other state, the stress is concentrated in this pleated region. So as soon as it forms a pleat, it eliminates stress from the body of the crystal and it concentrates it on the pleat.
I mean, usually, if I look at real materials,
Yeah.
if I take a two-dimensional sheet, let's say, of a layer material, then you see ripples.
Yes.
Okay. So how would this process?
This is slightly different because these ripples are linear instabilities.
Right.
But this is a phase transition. So
But there is a competition. Right?
yes. So, okay, I would suspect that much before these ripples appear, there could be an equilibrium phase transition between something which has no ripples and something which has ripples. But this thing should happen much before an instability occurs. I mean, if there is a first order transition, the equilibrium transition is always much earlier. And then once you are deep into the unstable phase, then these instabilities appear. So
sorry for this.
No, sir.
The reason is because I find this very interesting. So you have a two-dimensional system and you have done a simulation, right?
Yeah.
Now it is well known that if you increase the size of the system, only then you would see ripples, otherwise you would not see ripples.
That is very.
So may I submit to you that if your system size is not large enough, okay, maybe you have excluded ripples in your simulation.
What I would say is that if my system size is smaller than this, we don't even see pleats. And there's a reason for that. Because when you pleat, you also you have you strain the other parts of the system. And if your system size is too small, then the strain energy is too large. So for a very small, stiff crystal, you would not see this transition. So there's a systematics which I am not talking about here of system size. Yeah. So I agree with you on this. And as you increase the size, different configurations which were not possible in the smaller systems will become possible. Okay, so this elimination of the stress is very much like, I'm nearing my limit. The elimination of the stress is very much like a Meissner effect. Okay, so so this is sort of have been talked about in the literature, but not exactly in the way that we are talking about. So this is called the stress Meissner effect, and what this shows is a very interesting thing, that this Miura-OD tessellations in this model, they are just analogs of the Abrikosa vortex lattice. So in a crystal, in a quantum system, you have a vortex lattice. We have a classical system, and there the analog seems to be these tessellations, these pleated states. Okay, so now instabilities and dynamical transitions. Okay, so if you have an equilibrium transition, so this much was someone did something. Okay, so this was Monte Carlo. Now we do molecular dynamics. Okay. So if you do molecular dynamics, you never get these nice patterns, but if you get something, amorphous. The reason is that it is forever trying to go into these patterns. So these are the ground states, and it is trying to dynamically achieve these ground states, but it is taking enormous amount of time because to go from one pattern to another, you need to rearrange a lot of atoms. So, so once you are in some metastable state, it is very difficult for you to come out. So this is very similar to structural transitions in solids and so on. So where you see metastability as a sort of jammed configuration. Okay. So the other thing that I find very interesting is that when this dynamical transition happens, the value of this non-affine parameter is exactly this saddle point value. So as soon as the crystal reaches this saddle point value, it transforms. So there is an equilibrium transition and then there is this dynamical transition. Okay.
In the empty case,
yeah.
you're doing straight empty.
Yes.
Okay. But if you do metadynamics empty, you would be able to access the time scale.
Sure, but that, yeah, exactly. So we would be, yeah.
Because then you can overcome barriers.
Exactly, yeah. But we know that those barriers exist and everything from our Monte Carlo. So that's the, yeah, sure. So what is the connection between pleating and plasticity? I mean, the rest of the talk will go very fast, I assure. If you plot stress versus strain, then this pleating transition is exactly same as the origin of plastic irreversibility in this system. So if as soon as the object, the network pleats, you get a flattening of the stress versus strain curve, and if you release the strain, it does not follow the same stress. So it follows a different curve. Of course, there is only a finite number of pleats that this network can take. So after a while, once all those pleats have happened, it reverts back to an elastic continuum. So, but now this is a pleated elastic continuum. It's a slightly different object. What I would like to point out again here is that these different curves are at different values of h, but you can see that h does not change the elastic constants at all, because you can see that from the dynamical matrix which you can calculate analytically. H contributes to order q square in the dynamical matrix. So elastic constants are of order q. So to lowest order there is no contribution. Okay, and you can again do finite size scaling. So you can see that the stress versus strain is just a manifestation of this equilibrium transition which is underneath. Okay. So what does this say about normal solids? So this is, all of this was, some strange harmonically bonded network and so on. So suppose if you have a normal solid where this little red rectangle was replaced by a normal pair potential where we take Lennard-Jones pair potentials. Okay, so this is something that we know and love. So this normal 2D Lennard-Jones system, and there suppose we put in this field. So what happens? So if you plot stress versus strain in the presence of field, then you can see that by changing the field from positive to negative over 0, you can change the yield point without changing the elastic constants. So if you had a colloidal solid, you can actually change the yield point of this colloidal solid without doing anything else. Okay? And now we have a very good definition of the yield point, because if it is a dynamical transition and there is this variable, the collective coordinate, that shows a jump. And this jump also depends on the value of the field. Okay? So this is again exactly analogous transition. Okay, so there is this jump in this collective coordinate. I am not calling it order parameter for a very valid reason. And elastic properties are unchanged. If you were to look closely in this region, you would see that again the value of this quantity at the jump seems to be constant over some values of h. Okay? So it's sort of roughly constant. Now this gives us an idea. one can do linear response theory, okay, to find out how this quantity changes as a function of h. And linear response, as we know, they all depends on fluctuation terms which are calculated for h equal to 0. So suppose if you have a colloidal solid, you can without putting in any field, you calculate some susceptibility, some fluctuations, and these are easily accessible from particle coordinates and so on. And then you can predict that if I were to apply field, what would have been the value of h. Okay. Add to that one single criterion, which is the value of x at the saddle point. We know that for the harmonic solid, we don't know it for Lennard-Jones. For this particular density and temperature, we found out that it is around 0.2. We suspect, and these are calculations which a student is doing right now, we suspect that this can be scaled, and we suspect that finally there will be only one scaled parameter for any particular system. Okay, so this is the maximum non-affineness that a crystal can take. Once you have that, then you can calculate a phase diagram, a dynamical phase diagram, and this is this line. These points, and this is the line through the points. You extrapolate this line to hit h equal to 0. Okay? And these are the yield points which you calculate. The black points are the yield points which you actually calculate in a simulation. And you can see that you have a prediction of the yield point. Okay? Because this transition, this dynamical transition as a function of h or as a function of strain is the same transition. So this is the main point of this entire study. And this is sort of remarkable because you can actually now predict yield points from a Lindemann-like criterion. Okay, so one parameter, and that which should be, one can calculate it for various interactions. So imagine that you have, instead of, this whole host of dislocation interactions and so on, for copper, for aluminum, for Lennard-Jones, you have one parameter listed. You have 5 minutes, and then discussions. Okay. Yeah. So I'll. Okay. And then that gives you the yield point. It's somewhat more than that because there seems to be a very deep connection between a pleat and a dislocation dipole. So if you have a pleat, your displacement is single valued outside the pleat and multi-valued inside. This is similar if you have a dislocation dipole because there is a jump in the displacement as you go across this line. There is a branch cut, and this is just the Burgers vector. Okay, so there seems to be a deep connection. And this connection becomes more obvious if you look at the phase diagram. So here is the phase diagram for the network. A is the unpleated phase, B is the pleated phase. This is the equilibrium phase transition line. Okay, and this is the dynamical line. And you can argue that whatever be the interactions, this point has to be for positive h. Okay, so this dynamical line, the location can be different, but it always has to be at positive h. The equilibrium line can be anywhere because it depends on the free energies. So this is the case for pleating. Here is the case for solids. So we saw this dynamical line. Okay, we are actually calculating this equilibrium line right now. And this equilibrium transition is between two very interesting phases. A is a phase which what we think is a solid, that it resists shear. So you take a solid and you shear it, it resists. So that is phase A. Phase B is a solid which you shear it, it automatically rearranges and then gets rid of the shear. So it is not a liquid. It's by maintaining crystalline order, it can rearrange by moving dislocations here and there so that it rearranges and again sort of reappears as a crystalline solid. Okay? So there is no dynamics involved. This is just two states. So there is a solid which takes shear, there is a solid which does not take. I am calling this a solid because it has crystalline order. You can, if you assume this, you can actually calculate this boundary. Okay? So why did this calculation work, this Sauced-Birolli calculation? It can work only if all solids, all crystalline solids are actually in this metastable region. So they are really metastable. Okay, and this is something sort of dangerous to say. The consequence is that all crystalline solids are metastable because you can always reduce stress by rearrangement by paying only boundary cost. However, you can make them stable by putting in a field. So you can prepare a absolutely perfect solid only if you put in a field or if you attach bonds to them. So that is the only way you can shift the equilibrium line to the right. Okay, so that is the only way you can go into phase A, but otherwise you are always in phase B. Okay, so then this plastic deformation is just a dynamical transition associated with this equilibrium transition, and then we don't need dislocations for this description. Okay, so we can treat it as any other dynamical transition, and the yield point can be got with a single Lindemann-like input, and you can actually selectively tailor this. So I would like to end this part by saying that this fundamental cause of plastic deformation, fracture, basically might be that all crystalline solids are actually metastable with respect to non-affine fluctuations. That is a statement that we are all friends, and I am making this statement. Okay, I have a few slides left for the protein thing. Okay, I'll just show them. So how do non-affine variables work in proteins? So I have taken some 4 proteins here, and this is a map of non-affinity in the protein structures. So mind you, non-affinity, it captures interesting motions, and proteins have lots of interesting motions. Okay, so it just captures those motions which are important. That is what is the hypothesis, and that is what I wanted to say. That large non-affineness is associated with functional parts of the protein, and we are going to see how it works out. So what we do is these NAP gap plots, which was suggested by Vani, faculty of IMSc, in one of my earlier visits. So if I show these plots, then it turns out that those parts of the protein which have large NAP also have large gap, which means those part of the protein which have large non-affineness also have one particular motion which is distinguished from the rest of the non-affine motion. So there is one particular thing which is going on. Okay, so so we did this for very 22 different proteins, and I am showing it for one, and even the scales are the same. So these graphs, they look very similar, and then you can pick up some part which contributes, let's say, a large NAP and large gap region, and then go back to the protein which gave you that, and you find that this is very close to an ATP binding site. So this is this protein called 3L8P, and that is related, it's a part of a larger protein which is involved in angiogenesis. There's the formation of blood vessels, and this is, my knowledge is from Wikipedia in this. So, and then if you, by comparing all this, this is how we got to this point, and then what is this large NAP region doing? So this is a different view of the protein. Here is the ATP binding site. This site is actually inside the protein, surrounded, high density. So this site itself has low non-affineness. Okay. However, outside on the surface, there is a region which has large red atoms. So these are non-affine regions. And we looked at the most probable non-affine motions, and it's not very clear from this movie. We are trying to get better movies. But what this non-affineness is doing is sort of opening a door to this ligand binding sites. So what we are trying to propose, this will require much more study than what I have presented here. That so this has to do with this amino acid serine. So these are like doorways to the binding site. So we can identify doorways which actually open up and close. So, and this opening up is an interesting deformation which we can pinpoint using non-affineness. And as a last reminder, I should say that the non-affine parameter is actually only 2 to 3% of the total deformation. So if we just looked at the square of the displacement, we wouldn't have got anything. So it is really picking up the grain from the sand which gave us insight into this particular region in this protein. Okay, so this is very much ongoing work. So I leave with these comments, I'm done. So there's a single parameter which promises to give insights into all kinds of, it should be nano. Too much influenced by NAN. So, there's a single parameter which seems to be able to describe plastic deformation, pleating, protein structure, and it sort of spans mechanics to biology and possibly even fracture. Pleating of a sheet is a phase transition which is analogous to other kinds of phase transitions like Meissner effect and type 2 superconductors. Plastic deformation is a dynamical transition which is associated with this phase transition. And then, of course, this can capture functionally important motions in proteins. Publications, there are some which are going on. And finally, all of this work has been done by sequence of students. All the basic stuff was done by Shashwati, who is now doing a postdoc. And then this is being continued by Parsho. The protein work is being done by Dheeraj. And Dibankur has just joined, and he will be involved in this origami work together with Shashwati and some combinations. There are other students whose work which I did not talk about. Amartya is now a graduate student at Northwestern. He spent a year with me as an intern. Pankaj and Pappu, they are doing other problems, and this work is done in collaboration with Jürgen Horbach, Peter Solage, Smarajit, who is sitting there. Jagannath Mondal and Himanshu Khandelia are collaborating with me on the protein problem. And a lot of this thing came from spiritual discussions with Madan Rao through many years. And I've been funded by KITP, Indo-EU, OIST, CSIR, and so on. Thanks for your attention.
Number of questions? Yeah, sure.
This business of pleating, if it's 2 dimensions, you have a third dimension to lift it and then collapse it again. But in 3 dimensions, you have to maybe go to 4. And that brings to mind quasi-crystals, where with projection with an irrational angle, you can get things which are seemingly non-periodic or aperiodic from something whose origin, Platonic origin, so to say, is periodic. And can you think of this pleating in some sense as
we have had some discussions with Sriram and so on about quasicrystals and pleating in 4th dimensions becoming some structure.
Giving a geometric meaning to the projection.
It did not, I'm sure there is something, but we did not progress much.
The other point is this pleating has two corners.
Yes.
I mean, it's kind of reminiscent of unzipping of DNA, which is assisted by a temporary
Similar.
bubble.
Yeah. Yeah.
And then you have the notion that, see, it's like a dislocation dipole in two-dimensional melting or disclination.
Yes.
You can also, can you get the two ends or maybe to kind of unzip or move apart or unbind,
Yeah.
which would completely destroy the crystal presumably
Yeah. So.
and make a liquid.
Oh, so you are saying that there'll be lots of
See,
pleats.
I mean, we discussed this.
Yeah.
It's, if I take a path going around this dipole, I'll get zero.
Yes.
So on a coarse-grained level, it's a non-topological, non-affine
Yes.
region.
Yes.
So now I'm saying, can you look inside the pleat
Yes.
and destroy or expand the pleat in some way? Will that, or is that crystal to liquid transition?
So basically, you are asking whether we can go from order to disorder using this pleated. I don't know the answer offhand, but yeah, it's a.
That's a very good point, because
Yeah.
if you make the analogy with DNA unzipping,
Yes.
okay, that's the first order phase transition.
Yes.
That has been studied by
Yeah.
Charlie Kittel in '67.
Yeah.
So
Sure.
there's a lot of
There's
literature on
yeah. This can connect up a lot of other things.
Right.
Yeah. I think there was a question from there.
So in the context of metals, what you call the yield point is basically just the pair stress, right? Not
Yeah.
what you would get as the yield point in an experiment, right?
Yeah. So I think this will solve that problem too, because in metals, what is the yield point, that is controversial. Whether the beginning of beginning of the nonlinearity or the top of the stress maximum, and there are yield curves which show nothing. I mean, which are very smooth. Okay. What we are trying to say is that don't plot stress versus strain. Plot non-affineness versus strain. And there you should see something like a jump or at least a sigmoidal curve or something, and that will be much more well defined. So, because as soon as the first dislocation forms, as soon as the first topology change happens, this non-affineness should jump. So
your definition of yield point, there would be the first point where you get some.
No. So my definition would be to try to plot this this collective coordinate and see what that does instead of the stress. However, of course, you can plot the stress for any metal, but in a metal you don't have access to the atomic positions. Okay. So that is why what I am saying is not practicable for atomic normal materials, but for colloids you can do that.
I mean, this affine transition is not unique. I mean, so affine
Yeah.
matrix. So,
Yeah.
I mean, you mean that whatever I choose and then maximize or minimize with respect to that,
Yeah,
the eigenvectors will be independent of my choice.
they should be. Yeah, they should be.
Your
Yeah,
D should
Yeah.
not come.
yeah.
Okay, yeah.
Yeah.
You said that those who look at non-nonaffineness
Yes.
is functionally active,
Yes.
but those which are large non-affineness will be like somewhat soft region.
Yes.
Do you have a one-to-one correspondence between functionality
They
and
will
softness?
be, from studying these 4 proteins, this is a study which has just started. So we have 60 proteins and we have just done 4. So from these 4, what we are seeing is that if there is an important binding site, that site is usually inside the protein because it is a hydrophobic site. So that will be inside the protein, and that is an affine region. However, above that, on the surface, on the surface there will be something which will control access to that site. So basically what happens is that this thing opens up and then there's some phosphorylation or whatever, and then this binding site comes out.
In general, let's say when you have the big chunk of part of protein moves, right? Like if some ligand comes, when I comes over to the Jagannatha.
Yeah.
So it comes and the whole thing, there is a huge conformation change.
Yes.
So if you calculate non-affinity that point, then you will see that the whole protein itself has huge non-affinity.
Yes, so that is like acting it on with a field. So once you put a field, then this conformation shall change. So the analog of the pleating transition or the plastic deformation in the case of a protein is bringing a ligand close to the protein.
Okay, so we can continue the discussions during the tea. So let us thank again for this interesting presentation.